Hi everyone. Today we're going to be learning about what's called chemical equilibrium and how you can identify things about chemical equilibrium based on the equation that you are given, so a balanced chemical equation. How do we then write what's called an equilibrium expression, or what is called a KEQ, and see normally what you'll see it called, and then how do we actually calculate that value? So when we are looking at chemical equilibrium, so this is when we're talking about reversible reactions. So if you see something that's reversible, you would see these kind of arrows instead of just a singular right moving arrow. That indicates that the reaction can go back and forth from reactants to products to reactants to products, and it just keeps going back and forth like that until eventually it hits a point called equilibrium. So equilibrium is defined when it's the state where your forward and reverse reactions are balanced out. So you can kind of think of it like a seesaw or a scale. Equilibrium is where you're going to have equal rates of the forward reaction and the reverse reaction. So they're happening at the same rate and at the same frequency. So what we then look at with equilibrium is what is called the law of chemical equilibrium. So if we have a given temperature, so at a set temperature, chemical systems will reach a point where the ratio of product to reactant is going to be a constant value, meaning like I can tell whether or not something is at equilibrium if we've hit this, this constant, what's called a KEQ. So this is called the equilibrium constant. It's unitless. And essentially what we're doing is we're just comparing the concentrations of the products to the reactants and seeing which side of the equation the balance is. So are we going to have more products at the end? Are we going to have more reactants at the end? This is also all what we are told by looking at a KEQ value. So when you are trying to write an equilibrium expression, and I don't know why, for whatever reason, those arrows didn't copy over, but this fake equation that you see listed up here has these little numbers out in front and then these larger uppercase that are listed there. The uppercase ones are representative of chemicals in a chemical reaction, like water. And then these smaller letters are representative of the coefficients that would go out in front in a balanced chemical equation. So when we are looking at making a KEQ equation, we're going to put the concentration of our products over the concentration of our reactants. And then it goes to whatever power the coefficient is. So let's say I'm looking at this sample here. I would have the concentration of C to the C power times the concentration of D to the D power all over A to the A power and B to the B power. So essentially all it means is that these small numbers are what are going in the exponent. The big letters are the chemicals that we're looking at. So when we eventually solve these, put numbers in, calculate it, whatever else, you will find that you get a numeric answer. And again, this is unitless, but this numeric answer correlates to what's going to be more of at the end of the reaction equilibrium, more products or more reactants. If you have a KEQ of greater than 1, you're going to have more products. If you have a KEQ of less than 1, you're going to have more reactants. So it's just dependent on what your value ends up being and what it's then equal to. So if we're looking at this particular example here, there's two types of equilibrium that can be reached in chemistry. We can have what's called homogeneous equilibria. This is where they're all the same physical state. They're all gases, they're all aqueous, and that's what's shown kind of here down in that little area. So you would look there. So I look and see, okay, this first one, if we wanted to write the equilibrium constant, we're going to put our products on top, raise it to whatever power that coefficient is, and the bottom would have our reactant. So that's how you'd write the KEQ equation for this first one. If we wanted to do the second one a little bit larger, so we have CH4 times H2O all over CO. Oops, even I make mistakes. And then H2 to the third power. Okay, so that's how you'd write that equation. However, in chemistry, sometimes things aren't so nice and beautiful in all the same state of matter, and that's what we call heterogeneous equilibrium. This is where you're going to have more than one physical state, meaning gas, liquid, solid, aqueous. So it's going to be more than just one thing. One thing to keep in mind, and I'm going to put a little star by this, you should definitely know this. Solids or liquids do not change their concentration. So equilibrium is looking at how concentration is changing over time. So with aqueous solutions, you can add in more solute, concentrate it more, or you can dilute it. So the concentration is changeable. Gases, you can have more molecules of gas available or less in a given space. So that can change as well. Both of those, you can have increased or decreased concentrations. But for a solid or a pure liquid, if I'm looking at something like, let's say, copper metal, I can't make copper metal more concentrated or less concentrated. It's just copper metal. It fits in, the atoms fit in how they're going to fit in. So they do not have changing concentrations, meaning we don't include them. So we only do changeable concentrations in an equilibrium equation. So if you see that you have solids or liquids that are listed as like the state of matter down here in the equation, like I can see those are both solids, literally what you can do when you go to write this, cross it out, okay? Because you are not going to include this in the equilibrium equation. Instead, all you're going to include is what's left behind. So in this case, it's going to be just the concentration of CO2, okay? If we're looking at just a couple more examples here, I don't know why these arrows didn't go in. But we look at the first one. We don't want to include the carbon because it's a solid. We don't include solids. So the KEQ value is going to be CO to the second power over CO2. If I look on the next example, I don't want to include the copper because it's a solid. I don't want to include the silver because it's a solid, so I'm literally just crossing it out. And then the two that are left behind are the copper nitrate and the silver nitrate. So I would write its KEQ value, CuNO3, all over AgNO3. And then we're going to square that because we have that number there. Okay? So that's how you do it. Pretty easy. So just another example one is the following: a homogeneous or heterogeneous equilibrium. Because we look at our state of matter and we have more than just one type, it's going to be heterogeneous. And because it's heterogeneous, we don't want to include the zirconium, that's a solid. So to write the equation here, it would be this species over the I2 squared. And it's just that simple. So once you get to the point where you can write these equations and you're pretty comfortable with it, you then get to the point where we're going to start adding in numbers. So when you're trying to calculate an equilibrium constant, first thing you're going to do is write the expression for it. So if we look at this equation here, these are all gases. So everything's going to be included in that equation. So we're going to have N2 times H2, and that's going to be, I can't really see that, but that's going to be to the third power. So I'll put that there in a different color ink. All over NH3 to the second power. So this is the equation that I'm going to want to use. Then I'm given data in this data table that tells me what the concentrations of my reactants and my two products are at equilibrium. So we've reached equilibrium, everything's nice and balanced. The reaction is, just kind of hanging out right now. And then what we're going to do is plug in these concentration values into our equation that we wrote up here. So I'm just going to bring it down. We're going to put the N2 in the first set of brackets. Multiply that by, oops, I didn't want to put H. I want to actually put the number there. H2 is 1.600, but remember that's to the third power since we have that exponent there. And the NH2, 0.933, and this is going to be squared, again, because we have that number out in front there. So it might be tempting for you when you're looking at a problem like this to just plug everything in your calculator and press enter and hope for the best. However, if you look, we have this exponent and this exponent here. What you should do per order of operations is figure out what those values are first, then go through and do your multiplying steps. So that's what I'm going to do. So the 0.533 stays the same. 1.60 to the third power is going to become 4.096. My denominator, I'm squaring that 0.933, that becomes 0.870489. Then I can go through and do my dividing, and it's going to be equal to 1.9. So this value here, because our KEQ is greater than 1, that means there are more products at equilibrium. So if I was looking at, this equation, I would have more products versus reactants, and that's, what this equation can tell me. So hopefully by this point you understand what equilibrium is, the difference between a homogeneous and a heterogeneous equilibria, how to write those expressions, and then how to do the calculations. So let me know if you have any questions.